matrix method of structure analysis. Today we'll discuss some of the topics related to that. In that, before we go for this problem, we would like to go to some important topics. Okay, for that, now we'll go for the topics. That is, if you can see through this, so this are the formulas which we are supposed to remember. Okay, so please go through this. If you have a cantilever beam, okay, this is the cantilever beam. Okay, if this cantilever beam is existing, then what is the formula for theta value? Okay, these theta values are the slopes and delta values are the deflections which we consider with respect to flexibility and stiffness matrix method. Okay, so if we have a moment about Fdn, then the value of theta b is, or the slope with respect to the theta point b is ml by a, whereas delta, the displacement with respect to the member, is at point b is delta b is equals to ml square by 2a. Okay, similarly, if we have a point load, then the formula is theta b is equals to pl square by 2e, and theta and delta b is equals to pl cube by 3a. These formulas are important. These may be asked as a part of part B or else in any of the problems. So please make this as important and go to this. Next, if you have a cantilever beam with UDL support, then theta b is pl cube by 6a, whereas delta b is pl 4 by 8a. So next, if you have a simply supported condition, then the theta b value is, if there is a moment acting about point A, then theta a, the slope at A is ml by 3a, and theta b, which is at the far end moment, is ml by 6a. For theta is equals to 1, m is equals to 3l by ei by l. Okay, here you have a doubt when we have supposed to take the value of m as 3a by l and 4a by l. 3a by l is considered when the supports are hinged, foreign supports and near end supports are hinged to roller condition. Okay, foreign, here forward condition is roller condition, so we are taking as 3a by l, m value, and theta a is equals to 1. Sorry. So similarly, if we go for the fifth one, you have if we go for fifth one, then we have two moments acting at the ends with the supports, and theta a, theta b will be ml by 2ea. Okay, and delta c is ml square by 8e. Okay, whereas for the same simply supporter, if we have a point load at center, then theta a and theta b will be pl square by 16a. Delta is pl cube by 48a. If you have a point load acting eccentrically, okay, at a distance of a from support a and b from support b, then the theta a value is pab into 2l minus a by 6l a. Okay, if this is slope at a. Next, if it is at theta b, then pa into l square minus a square by 6l into ea, whereas delta c is p into a square b square by 3a. Okay, Next, if it is a uniformly distributed load, then theta A and theta B values are PLQ by 24 EA and delta C is 5 PL power 4 by 384 EA. Okay. Next, if we go for a fixed beam condition, okay, we have a fixed beam with point load at center, then MA value, moment about A and moment about B are, because in the previous cases all are simply supported or cantilever, for which you will have the slopes at any of the points. Here at the fixed ends you don't have slopes, because about fixed supports the slopes are zeros. Hence MAB is equals to MBA we will be considering as PL by 8, whereas delta C, that is displacement at point C, is PL cube by 192 EA. And if you have a point load with a centrical loading condition, then as usual you know the formula, P into AB square by L square. MB is equals to PB into A square by L square, and delta C is PA cube B cube by 3 L cube EA. If you have a UDL for the same fixed support, fixed beam, then MAB is equals to MBA. MA is equals to MB is equals to PL square by 12 EA. Okay, and P delta C is PL power 4 by 384 EA. Okay. Next, if we have a moment acting about A, then MA is equals to, if the moment is about B, and then the moment about A is equals to M by 2, whereas theta B is equals to ML by 4 EA. Okay, and RA is equals to 1.5 into M by L. Okay, for theta B is equals to 1, then M is equals to 4 EA by L, MA is equals to 2 EA by L, because M is equals to near end moment about A, about here, and the foreign moment is 2 EA by L. Okay, R is equals to RB, that is equals to 6 EA by L square. Next, if we have a displacement about point B or sinking with the support in the fixed beam, then MA is equals to MB is equals to 6A delta by L square, or 6A 5 by L. Okay, where 5 is equals to delta by L, RA is equals to RB is equals to 12EA delta by L cube and 12EA 5 by L square. Please note these values, because if delta is equals to 1, 5 is equals to 1 by L. Hence MA is equals to 6A by L square and RB are 12A by L cube. Please remember these reactions, because these are much more important when we go for displacements. Right? With this we'll end, and we'll go for some other concepts as well. Yeah. What is the difference or the similarities which we find with respect to two methods, that is flexibility matrix method and stiffness matrix method of analysis? So, coming to the flexibility matrix method, okay, here during the flexibility matrix method, as we know that we are supposed to find the degree of static indeterminacy, or we call it as degree of redundancy, whereas for this the degree of freedom or degree of kinematic indeterminacy is considered as priority. And Next we will find the choose the redundants. Okay, here we will go for identifying the independent displacement components. Next, assigning coordinates. This is with respect to the redundants, we will apply the coordinates. Okay, for if we have a matrix form of 3 by 3, then if you will take coordinate sets 1 2 3, for which where the forces are released or considered. Okay, next, in the same case for us independent conditions, assigning coordinates to the independent displacement components. Okay, already existing free forces whatever are there, for that you will assign the coordinate numbers and apply the unit forces. Next, removing all the redundants to obtain the released structure. Okay, so whatever the coordinates you have assigned, for that you will remove the redundants and then find the obtain the structure with released loads or released redundants. Next, preventing all the independent displacement components to obtain the restraint structure. So to obtain this restraint structure, we will consider prevent all the independent forces, because the structures whatever we go for analysis are of indeterminate, so we are making it to determinate by using this analysis. Next, fifth point, determine the displacements at the coordinates due to the applied loads acting on the release structure. Okay, so using delta L we will find the displacements coordinates due to applied loads. That is, we will take the conjugate beat concepts and then we will find the values, that is m by EI formula. Okay, whereas this m by EI formula or the delta L values, just now we have seen it the tabular form, so for the cantilever simply supported and fixed beams that we are considering here. Next, determine the forces required at the coordinates in the restraint structure due to the loads other than those cases acting at the coordinates. Okay, so if we have a point load in this section, the same what we do is we will find out using the formulas, that is loads WL square by 8, WL square by WL by 4 or whatever it is, if it is a point load, if it is UDL, and if it is a varying load, then based on the different loadings acting on the frame we will apply the load form moment formulas and then find out the values. Okay, next, sixth point, determining edge, the displacement of the coordinate due to the redundants acting on the releasing structure. So these are the determining redundants acting due, this delta R is the redundants which are acting due to the displacements which are acting due to the redundants. Okay, so next, determine the forces required at the coordinates in the unrestrained structure to cause the independent displacement components. So here we have found some released independent forces, right, due to the displacements or whatever it is. The forces P of delta, that is P1 and P2, so whatever it is, we'll find those values. Next, compute the net displacement at the coordinate, that is delta L plus delta R. Okay, and next compute the net forces at the coordinates. P is equals, matrix P is equals to P dash plus P delta matrix. So using the conditions of compatibility of displacements to compute the redundants, that is, we will form the matrix form matrix P is equals to delta matrix inverse into capital delta minus delta L. Okay, whereas in the stiffness matrix method of analysis, using the condition of equilibrium of forces to compute the displacements, there is the matrix delta matrix is equals to K inverse into P minus P dash. Okay, here next, knowing the redundance, complete the internal member forces due to equations of statics. Now in the displacement, compute the internal member forces by slope equation method. Okay, after finding all the matrix forms, then we'll go for using. So with this we have completed the differences between matrix method of analysis and stiffness method of analysis, that is flexibility and stiffness. Okay, next we will go for some other couple of formulas. Okay, just a minute. Here, as you know, that every member force is released if suppose either it is a stiffness matrix or flexibility matrix. We have three conditions of load applications. What are those three conditions? One is horizontal load, one is vertical load, and next one is movement. Okay, so let's go for a problem, then you can model thing, so you can get clearly about this. So if this is a member, okay, a spring which is having a free end, and one end of the spring is connected to support A and the other end of the spring is free. Okay, so a unit force or the force is applied at point A, then what point B at 1. Okay, if you go for diagram 4.1a, you can see the spring which is fixed at one end and the other end is free, and if a force P1 produces the displacement at coordinates 1, so this one coordinate represents the displacement which is acting. So due to this displacement, normally a free joint has three displacements. One is the horizontal displacement, if you can see in 4.1b. One is a horizontal, one is a second is a vertical, and third is a moment, and fourth is a torsional action acting on it. Okay, or twisting moment or shear, you can say it is. So for these different types of loadings, so how do we consider the formulas or take the formulas is by using these formulas. If you have a axial load acting on the frame, then types of displacements are, if it is a flexibility, then we will consider the axial loading condition. That is, if we have axial loading condition, then we will take L by A or AA by L. If it is flexibility, it is L by AA. If it is stiffness, it is AI by L. When you go for the next transfers, it is, if it is far end moment, then L cube by 2LAA, and if it is stiffness, 12AA by L cube. There are the reverse condition. If far end is hinged, then L cube by 3AA, and stiffness, it is 3A by L cube. Okay, if it is bending moment, L by 4A, 4A by L. This you know as usual. Okay, far end hinged, if it is L by 3A, 3A by L. If it is a torsion, L by GK, GK by L. So these formulas we are supposed to remember. As you have seen the transverse condition moment formulas just now over there with respect to simply supported. Actually the formulas are derived from here. If you can go through, it is a axial load, then delta is equals to PL by A. This you know that, I think, yeah. So PL by A is the formula from which a kilonewton, 1 kilonewton of load is acted upon by the P. Okay, unit load is applied, then delta L1 becomes L by A, whereas K is AA by L. Okay, delta and K are similar, but the change is ratio of, that is inverse of flexibility is the stiffness. Okay, inverse of flexibility is stiffness. When you go for transverse, in the first case this is axial load which is acting here with the first case. Okay, so this is the first case, that is axial load. This is the transverse case, second case, and this is the third case, bending, and the fourth case is torsion. Okay, please remember this. Okay, so due to the transverse force P2, if you apply a kilonewton P2 at point B, then the value is 12EI delta 2 by L cube, and delta 222 is L cube by 12EI. Next, K22 is 12EI by L cube. And if it is a far end condition, if it is hinged with far end condition, then the formula is P2 is equals to 3EI delta 2 by L cube, and delta 22 is L cube by 3EI, and K22 is 3EI by L cube. Next, P3 is equals to 4EI delta 3 by L, and delta flexibility matrix is delta 33 is equals to L by EI, and delta K33 is 4EI by L. If it is near end moment also, then the value is 3EI by L. Far ends are hinged. As just now we have seen at the simply supported condition, how do we get the values of 3A by using this formula? If the far ends are fixed, this is the condition. If the far ends are hinged, then the formula is 3A by delta 3 by 3A delta 3 by L, whereas delta 33 is L by 3A, or K stiffness matrix K33 is 3A by L. If you have torsion or twist in the condition, delta is P4L by GK, and the torsion flexibility is delta 44 is L by GK. Now torsional stiffness is KK is equals to GK by L. Okay, so with this we'll end the important concepts related to that. Okay, so next we'll go on with the problem.